Hi, this video is about potential energy diagrams. We've been looking at chemical reactions for a while now, and we just say, hey, here are the reactants and here are the products. Now we're going to look at how those reactants go from reactants to products by looking at a diagram. And the one thing I really want us to learn from this video is to know that reactions are only going to occur if there is enough energy. So let's go ahead and start talking about factors that will affect our chemical reactions. So first of all, the reactant molecules that you're starting with, they have to collide in order to react. They have to run into each other. Not only do they have to run into each other, but they have to run into each other with enough energy to overcome what I call an activation barrier. And we're going to talk about that when we look at these potential energy diagrams. Well, if they have enough energy, they also have to have the right orientation. They have to be lined up in just the right way in order to react. And then, if they collide with the right orientation, with enough energy, their bonds will be broken, and then the bonds in the products will be formed. So a chemical reaction is nothing more than bonds breaking and bonds forming. So let's go ahead and look at a potential energy diagram. So a potential energy diagram is a graph, and potential energy is over here on the y-axis, and down here it's called the reaction. A lot of times I'll just say reaction progress. It's basically a timeline. And so we're going to start with our reactants at some potential energy. So this would be our reactants right here, reactants. Where we're starting, reactants. Okay, and then potential energy diagrams have this general shape. There's always a big hill right in the middle. And then the energy goes down. So notice the energy goes up and then the energy goes down. And over here where we end up in our reaction progress, that is the products. Now the first thing I want to talk about is the energy of where we started and where the energy, what happened to the energy at the end. In this particular potential energy diagram, that energy change we're going to call delta E. And the delta E in this reaction, the products is lower in energy than the reactants. And so our delta E is negative. Remembering that delta is products minus reactants, so small number minus bigger number gives us a negative value for delta E. Sometimes delta E is called the enthalpy of a reaction or the heat of a reaction. All right, so that's just looking at the change in the energy from where we start and where we end up. Okay, RXN is my abbreviation for reaction. All right, now what about this big hill right here in the middle? Well, the amount of energy that it takes to get from where you start, the energy of your reactants, to get to the top of that hill has a special name. And that name is the activation energy. And the top of the hill has a special name. At the very top up here, that is called our activated complex. And it used to be called a transition state. I haven't really heard that much lately. Activated complex. That is where bonds of the reactants are being broken and bonds of the products are being formed. All right, let's go ahead and define activation energy. Activation energy is the amount of energy required for the reactants to reach the activated complex. Activation energy. Remember we said in an earlier slide that the molecules must collide to react, and they must collide with enough energy. They have to have enough energy to get to the top of that hill. If they don't collide with enough energy to get to the top of the hill, they're not going to form products. All right, now let's look and talk about something we haven't really talked about before. All right, if we've got our reactant, we're just going to make them up, A plus B, and this would be a synthesis reaction forming AB. And so let's just go ahead and draw a potential energy diagram for this. Okay, so here's our reactants and here's our products. We call this the forward reaction. Okay, now The reverse reaction would be AB going back to A plus B. So we're reading it in reverse from right to left. And so that would be a decomposition reaction, wouldn't it? And so we can read these graphs then. We can see this is the products. So here's our forward reaction. And then the reverse reaction would be the products going back over the hill this way to the reactants. So when we start talking about the reverse reaction, we're talking about the products going back to form the reactants. Okay, now let's talk about an endothermic reaction. From our past, we know that an endothermic reaction is one where energy is absorbed from the surroundings, and then the surroundings feel cold. Endothermic reaction. Okay, so energy is being absorbed. So where we end up, our product should have higher energy than our reactants. And so again, this is energy, this is our reaction in progress down here. And let's draw a potential energy diagram for an endothermic reaction. Aha, look, the energy of the products, that's here, energy of the products is higher than the energy of the reactants. And so we would say that delta E here, and we can also have, values on our y-axis here. We could actually read the graph and read off numbers, and we'll practice that in class. But delta E for this is going to be positive, and it's endothermic. Again, the name from where we start in energy to the top of the hill is the same thing. We call it the activation energy, and our activated complex is up there. But this would be what a potential energy diagram looks like for an endothermic reaction. Let's look at one for an exothermic reaction. Okay, again, an exothermic reaction from the past, we remember that an exothermic reaction is where energy is released and they feel hot, or the temperature would be going up. So here's the energy of our reactants. We got to start here. And then in an exothermic reaction, we still have that activation energy. We have to get to the top of the hill. And then here is the energy of our products. Again, here our delta E is going to be negative. This is an exothermic reaction. We are ending, our products are at a lower energy than where we started. Now let's have a look at this really quickly. If we looked at the reverse reaction, first of all, let's look at the forward reaction. Our forward reaction is exothermic. We're ending at a lower energy than where we started. Now let's look at the reverse reaction. Let's go from right to left. What was that? We're ending at a higher energy than where we started in the reverse reaction. So here our reverse reaction is endothermic. So on this graph, our forward reaction is exothermic. See, ending at a lower energy. And then the reverse reaction is endothermic. All right. Now, what does a catalyst do? Well, it speeds up a reaction and it's not consumed in the reaction. Catalysts work by lowering the activation energy required to reach the activated complex. So it will speed up both the forward and the reverse reaction. In biology class, you call these guys enzymes. So what does a potential energy diagram look like when you add a catalyst? All right, well here we're going to go ahead and have an uncatalyzed reaction. All right, is that reaction exothermic or endothermic? It's endothermic. Excellent. Notice that we ended at a higher energy than where we started. So our forward reaction is endothermic. Now let's add a catalyst. A catalyst works by lowering the activation energy. So I'm going to draw a dotted line for what a catalyst does. It doesn't change the energy where we start. It just lowers the hill. And it doesn't change the energy where we end. The catalyst simply lowers the hill. And so that's how it speeds up the reaction. So these reactant molecules don't have to get all the way to this activated complex, the activated complex has been lowered. And notice for the reverse reaction, the Hill is also lowered. But it doesn't change the delta E of the reaction. The energy where we started and where we ended were the same. Okay, let's draw another potential energy diagram over here. And you know me well enough, you probably said, oh, she's going to draw an exothermic reaction. Yep, I did. Okay, there's our exothermic reaction. So this one was endothermic. This one is exothermic. And a catalyst works by lowering the Hill. So here is what the catalyst would do. It just lowers the activation energy required. And there we go. Just lowers the Hill. All right, so with these potential energy diagrams, be sure that you can define activation energy, the amount of energy required to reach the activated complex. The activated complex, the top of the Hill, that's where the bonds of the reactants are being broken and the bonds of the products are being formed. Know that a catalyst will lower the activation energy. It just lowers the Hill. It's all that it does. And the change in energy of a reaction, known as the reaction enthalpy or heat of a reaction, that's just the difference in energies from where you started and where you ended, and be able to look at a reaction profile and say if it's exothermic or endothermic. If you can do that, you've got this. Bye.